Hello, everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much, much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and would also greatly appreciate if you consider supporting us as well. So please check the link in the description for more details. My name is Sava, and today we're going to investigate the KPSS test, a very handy statistical procedure that can allow you to determine whether a time series is stationary or not, for example, whether it has a unit root. And it has been developed to augment the perspective of other stationarity tests, such as the DK Fuller test, a video on which we have already had on the channel, so please check this out if you're interested in DK Fuller. But KPSS is so different to other stationarity tests that it's always, or almost always, worth applying it alongside its counterparts to augment the perspective, to provide some additional insights into how the time series behaves across time. And we'll evidence the power and the concept and the maths behind the KPSS test by looking at three key macroeconomic aggregates provided by the Bank of England in their dataset A Millennium of Macroeconomic Data. We have got unemployment, inflation, and GDP growth figures for more than a century, starting in 1855 until 2016, so 162 years worth of data. So let's apply the KPSS test to all three of those in quick succession and investigate what is it all about. So first of all, starting with unemployment, we see the raw data over here, and we have to transform it somehow to apply the test. And there are two choices. You can either test whether the time series is stationary around a constant, or whether it's stationary around some time trend. And we'll investigate both. So first of all, to test whether it's stationary around a constant, we just have to calculate the average unemployment across the whole sample. Easy enough. We can just apply the average function to the whole array of unemployment figures and see that the average unemployment across the years is roughly 5.28%. And then the residual in the constant specification would just be the unemployment in a particular year minus the average unemployment throughout the sample. And we can log the row here. And then we bottom right click it all the way down and get our residuals over here. If, on the other hand, we want to test for stationarity around the trend, we can easily estimate the intercept and slope of a linear regression of unemployment onto the trend or any time variable. And here, it's quite handy, we already have years over here, so we can simply regress the unemployment figures on the year number. Or alternatively, we could have coded a time variable starting with 0 and adding 1 in every consecutive year, but that wouldn't change the results, so we can just stick with the year variable over here. So here, for constant and trend, in the trend specification, we can use the slope and intercept functions that are readily available in Excel. So first of all, for the trend, we can simply use the slope function and input the y variables, which are the dependent variables, that is the unemployment figures, and the x variable is going to be just the year array, the year column over here. And we can enforce this formula and see that the trend overall is positive, meaning that unemployment is more prominent in the UK economy later on down the line. And here, for the intercept, we can also use the intercept function and apply exactly the same logic, referring to the array of unemployment figures, the column of unemployment data, and the column with year numbers, and get the constant, the intercept of minus 24.83. It might surprise you or alert you that it's negative, but bear in mind that we start in year 1855 and not in year 0, so that shouldn't be too much of a problem here. For the residual in the constant plus trend specification, we have to subtract the expected value as per this regression equation from the observed value of unemployment. So let's just subtract, opening the parentheses, the constant with row locked plus the trend coefficient with row locked multiplied by the year number. And here we would have our residuals in the constant plus trend specification. And here, having calculated the residuals, it's already quite important to understand what the concept and the maths behind the test is. So here we are interested in knowing how stationary the data is. And what is different with KPSS is that, unlike in all other tests, the null hypothesis of KPSS is the time series is stationary. So the test statistic is low or close to zero when the time series does not demonstrate any persistent behavior, any random walk-ish behavior. And if the statistic is high, then the null hypothesis is rejected in favor of the alternative hypothesis that the time series is not stationary. For example, that it has a unit root. And the idea is to calculate cumulative residuals, that is ST, over here the notation is quite simple, across the whole sample. So we start calculating cumulative residuals for both specifications, starting with the first residual, and then adding up the next residual to our previous value of the cumulative residual. So those are just cumulative sums. And unsurprisingly, at the end, they revert back to zero, simply because the sum of all residuals in any regression is equal to zero. However, what we're interested in is in the path that the residual goes through throughout the sample. And the furthest it departs from zero across this path, the more reasons we have to believe that the time series is not stationary. And we can visualize it using the graph here. Here is the path of the cumulative residual in a constant plus trend specification, and we can see that it does actually fluctuate around zero quite a bit during the early years and the later years. However, there are some notable spikes in the war years and in the 60s and 70s. So this can already alert us towards the fact that there might be non-stationarity in the unemployment series. However, to formally test for that, we have to compute the KPSS test statistic. And in the numerator, we have got the squared sum of those cumulative residuals. Basically, we are looking at by how much it departs from zero in any way. We're not worried about either negative or positive values. We're just interested in the deviation from zero. And in the denominator, we have got the number of observations n squared and lambda squared, with lambda being the standard error of our residual. So here we simply adjust for the fact that the more observations we have, the more chance we've got to deviate from zero, isn't it? So we kind of level the playing field. And also, the more volatile the residual is, the further away it can depart from zero, all other things held constant. So here we extract the scale-independent statistic that can be treated as a measure of stationarity or non-stationarity. The higher it is, the further away from stationarity the time series is. So without further ado, let's calculate the squared cumulative residuals, the sum squared of the respective columns. So we can just apply the sum squared function to this particular column in the constant specification, and dragging it across, we'll immediately get the same value for the constant plus trend specification. And now we can calculate the standard errors, bearing in mind that we have to adjust for the degrees of freedom reduction. So in terms of the standard error for the constant specification, we have reduced the degrees of freedom by only one, as we have got one coefficient, it being the constant. So we can apply the sum squared of our residuals, not cumulative residuals in that case. Then we can divide it by the count of such residuals minus 1. Here minus 1 is again the degrees of freedom adjustment. We subtract 1 because we imposed one restriction onto the data. And to get the standard error and not variance, we can take the square root of the whole expression. And we get 3.03 as the standard error, meaning that on average in the constant specification, unemployment deviates from the mean by roughly 3% on average in every single year. Now we can drag it across and here substitute minus 1 to minus 2, simply because in the constant plus trend specification we have got two coefficients that are our degrees of freedom reductions. And we can see that the standard error is a bit lower, simply because the trend does explain quite a bit more fluctuations in unemployment over the years. And now in terms of the number of observations, we can simply count the respective residuals, and we're good to go to calculate the KPSS statistic. So here we just apply this particular formula. Given the fact that we have got the formula over here, we can simply divide the sum of squared cumulative residuals by number of observations squared times the standard error, lambda squared. And we get the KPSS statistic of 1.2. and then we can drag it across, and for the constant plus strength specification, get a KPSS statistic of 0.435. What we have to do next is to compare those obtained values, those observed values of the KPSS statistic, to the critical values that have been tabulated by the authors of the test: Kwiatkowski, Phillips, Schmidt, and Shin. And that's why this test is called KPSS, that's just the initials. So they have tabulated those critical values. Unfortunately, we cannot calculate them directly, so we just have to look them up in their paper or in some other internet source. And as we can see, the critical values for the 95% and the 99% confidence interval are, in both cases, much lower than the observed values of the statistic we have calculated. It means that the null hypothesis that the time series is stationary, that is, the deviation of the cumulative residual from zero are negligible, should be rejected in favor of the alternative hypothesis, the time series is not stationary, that it perhaps has a unit root. And here we can actually see how KPSS works well in combination with Dickey-Fuller augmented Dickey-Fuller. Whereas the augmented Dickey-Fuller, or Dickey-Fuller, has a null hypothesis that the series has a unit root, an alternative hypothesis that it doesn't, the KPSS has a null hypothesis of stationarity and the alternative hypothesis of non-stationarity. So if you apply both tests at the same time and have a significant result for KPSS and an insignificant result for Dickey-Fuller, you can be very much sure that you have got a unit root on your hands. If, on the other hand, you have got an insignificant result for KPSS and a significant result for Dickey-Fuller, you again can be very confident that you stumbled upon a stationary time series. Whereas, if you have got mixed results for two tests, you stumble upon a gray area, and you have to be extra cautious when operating with this particular series. However, we have got two final steps to take. Let's see how unemployment, in terms of its stationarity or non-stationarity, compares to inflation and economic growth series. So we can simply copy the inflation series and paste it over here, and our results will immediately recalculate to show that in terms of the KPSS statistic, inflation is still very much non-stationary. And that is quite a common observation in macroeconomics, that unemployment and inflation are non-stationary time series. They have some dependence in them, so you cannot model them as a non-autocorrelated, a stationary time series. However, if we look at economic growth figures, copying that over here and pasting it in place of inflation, we can see that the statistics for economic growth are much lower. They are even lower than the 95% critical value, meaning that economic growth figures are more stationary and stationary as per the test results, meaning that for economic growth, you can be reasonably sure that it is not that much autocorrelated, for example, as inflation and unemployment. And that's all there is for the KPSS test and its applications to detecting stationarity and non-stationarity in macroeconomic time series. Obviously, you could also apply this test to other time series, financial, for example, stock prices or stock returns. Nothing prohibits you from that. And that's the beauty of it, how flexible, simple, and intuitive it is. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions in videos for business, finance, or economics topics you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.